Thank you for the introduction. Good afternoon. So in the chart that I'm representing here, we perform reservoir simulation for robust optimization, and also we intend to incorporate in the reservoir simulations a phenomenon related to geomechanics and geochemistry. And the reason of that is because of the pre-salt reservoirs that my colleague Erwin Mackay mentioned this morning. In these reservoirs we have considerable production of CO2 that must be reinjected. The CO2 cannot be released to the atmosphere. So we have injection of CO2 alternate with seawater, so it's a WOG process. And this mixing of CO2 and water will form carbonic acid that will dissolve the carbonate rocks. It's a fractured carbonate rock, and will affect the near field of the injector. So the sponsor of this research, that is the research that I will present today, is worried about the long-term injection of CO2 alternate with water. It's this reservoir, we have many years of production from now, and it's already half of Brazilian production, of the total Brazilian production. So before I talk about this water weakening phenomenon, that is the change of properties, not only porosity and permeability, but also the geomechanical properties due to mineral dissolution, I prepare a slide that summarizes our contribution of our chair to the industry in the last 10 years. That is the time that you have our chair program. So in this first, in 2008, we had the opportunity to apply our fully coupled hydromechanical finite element code to perform elastoplastic analysis of fault reactivation. In this case, the objective is to determine the maximum bottom hole pressure that will prevent the fault reactivation. So, and this is a research line that is still active. Very recently, last year, we performed submarine landslides analysis triggered by fault reactivation and reservoir compaction. And also, we have a project that the objective is to incorporate geological information from outcrops, in this case, the formation bands in the core material in the core layer of the fault. So fault is a complex geological structure that we incorporate more complexity as we are working in this area. After that, we had the opportunity to apply our reactive transport formulation to the caprock integrity problem. This is in the post-salt, the fault reactivation in post-salt, it's above the salt layer. And in the caprock integrity analysis, we evaluate the dissolution of the caprock, that's sodium chloride rock, due to water injection. So we use our reactive transport analysis to identify a safe depth for the injectors, for the completions of the injections that will limit the dissolution of this caprock. We are now working in collaboration with our geology department at our university in outcrop data for fractured carbonate analogs. For instance, to build discrete network fractures for this for the simulations is a pre-salt analog, and we have a a program in our very recent rock mechanics lab that I will show the results in a few minutes. And finally, we have this cave in Salt Domes project. It's very recent. We are in the beginning of the project, where the idea is to build sets of caves using the solution mining technique, that is injection of seawater and production of brine. So you have caverns that will be connected, and the idea is to store produced fluids as auxiliary reservoirs for this reservoir. So the reason of that is these reservoirs, the pre-salt reservoirs, are about 300 kilometers from the coast. So it is a logistic problem how to store and send all the production to the land. Finally, we are finishing an interesting project that is the reinjection of produced water in the. It is in north part of Brazil, in Amazonas area, and the problem here is the reinjection of produced waters in the Ticuna aquifer. This was a requirement of ANP, National Agency of Petroleum, that impact study must be done to see the impact of this reinjection in this aquifer. And it's a huge aquifer. It's in 4 countries: Brazil, Peru, Ecuador, and Colombia. And together with the Federal University of Rio de Janeiro, they build a geological model. We simulate this aquifer. We obtain the regional flow through the aquifer, and then we proceed the simulation of this high salinity water with variable density flow, and we are finishing. The impact is very low. There's almost not a drop in an ocean of water, drop of saline water, but it was done, and it was a requirement. So back to the pre-salt area, back to the water weakening problem. We have this CO2 injection in the mix with water, acidification of water, and dissolution of calcite, for instance. So part of the solid phase will be dissolved, and there are some consequences. Change of rock porosity and permeability due to mineral dissolution precipitation, change of roughness and fracture opening, and in general, change of the geomechanical behavior of the rocks and fractures. And to perform an analysis of this phenomena, it is necessary to consider the geomechanics. Some relevant phenomena for geomechanics are shear and dilation, induced anisotropy, pore collapse, fracturing, pressure propagation, and we also are including the chemical process. In this case, we have to solve, coupled with geomechanics and fluid flow, the reactive transport. In the reactive transport, we have to solve the transport equation of each one of species dissolved in the aqueous phase, considering the chemical reactions. Chemical reactions can be fast, so we use chemical equilibrium model, and also can be some reactions, dissolution and precipitation reactions can be also slow, so we have also to incorporate in our geochemical model kinetics. So in our workflow, research workflow, we are trying to integrate numerical simulation, lab experiments, and outcrop data. This is a very nice outcrop that we have here fractures at different scales, and we map the fractures, and we were able to build a DFN generator for our models. And in the lab experiments, we are trying, so this is the topic that I would like to talk a little bit more. We are trying to obtain experimental evidence of this coupling between geochemistry and geomechanics and this up to now, it's a very basic study. For instance, it is one of the first PhD thesis that we had in this problem. We simulate a test, odometer test proposed by Keane and Santa Marina. In this test, we put a sample. In this first experiment, we consider the porous media composed by glass spheres as the non-reactive mineral and sodium chloride as the reactive mineral that will be exposed to water. And the water will dissolve the sodium chloride. So you have some chemical reaction, dissolution of the mineral. And this was done under a constant load in a odometric cell where we apply a constant vertical stress. Lateral stress are prevented, and we have here strain gauge that will measure the lateral stress. So what we observe when dissolution takes place is that we have a decrease of the volume of the sample. So we have a vertical strain that is observed, and we have also the change in the lateral stress. In this case, we can observe the decrease of, in the beginning, we decrease of lateral stress due to the grain mass loss, but at a certain point, we have a rearrangement of the internal granular structure of the material, and we have an increase of the lateral stress, and to a point that it's similar to a value similar of the beginning of the test. So to illustrate this kind of phenomena, we're using modeling. We incorporate in our geomechanical model elastic induced strain deformation due to the total mineral volume. So if the total mineral volume decreases, we have a shrinkage of the material, and we incorporate in our elastic model. So in our simulation of the sample, we have a dissolution front of the mineral. We have a non-uniform stress state inside the sample, and we could model the decrease of volume, the vertical strain of the sample, and also the decrease of the lateral stress. But we are up to now, we are not able to model the increase of the lateral stress. In this case, if we consider some elastoplastic, irreversible mechanisms, we put the Moore-Coulomb model here, for instance, the simplest elastoplastic model, one of the simplest classical elastoplastic model, we could inside the sample develop elastoplastic deformation for dilation, so that increase the lateral stress, and but not at the point of the beginning of the test. So to control the increase of this lateral stress, we can induce some degradation of the material during the test. For instance, the decrease of cohesion. As the vertical stress remains constant during all the test, the only option for the lateral stress when the cohesion decreases is increase its value. It's because of the consistency condition that comes from the elastoplastic theory. So this is a very simple test that we can interpret using basic geomechanics model, that we can conclude that, or you can consider that at the well and reservoir scale, if you have rock dissolution under a constant load or a more or less constant stress state, we can have chemical induced reservoir compaction, and we can have also degradation of the material that will affect, for instance, wellbore stability and faults and fault reactivation and so on. So we are now performing this same test for artificial carbonate rock. We are using artificial carbonate rock because we want a pervious and high porosity and pervious carbonate rock, and we also want repeatability of the test because the objective is to build constitutive models, and this is a work that is conducted by the PhD student Katia Botelho that is here, and she exposed this sample to acid, and we had the solution under constant load. We have here the tomographic images of these samples before and after the solution. And we, in this case, use a more sophisticated elastoplastic model based on the critical state theory, where we have two effects in this case. When the solution takes place, we have the decrease of the pre-consolidation stress, consider here a cap, and you have also the decrease of tensile strength. So we are able to model a more complex behavior of the material. And what we can see here is that with this model, we were able to validate very well this model with the experimental data generated by Katia. Katia also worked with injecting fluids through artificial carbonate rock with fluids with different pH, with in the beginning a very aggressive solution, pH 2, that form wormholes. We are not interested in wormholes. We would like to have a very uniform dissolution of the sample, as we want to build models, a constitutive model for that. So we increase the pH. We have more or less a better dissolution, more uniform dissolution, pH 3 and pH 4. And after this dissolution tests, Katia did perform uncompression and confined compression tests, and we can see here that the chemical attack, the dissolution, decrease a lot the strength and stiffness of the samples. And if you compare the samples with pH 3 and pH 4, we can see that higher the chemical attack, higher the decrease of strength and stiffness. We have more results right now that confirm this behavior, and we discard this pH 2 sample because of this wormhole. And we are also observing the same pattern for the tensile strength of the material. Another student, that is Minel, she is working with these samples from this crater formation, the crater formation that is analog to the pre-salt, and she is performing the direct shear tests with in apparatus that we adapt for plugs with a fracture, and we perform direct shear tests for samples without a chemical attack and with a chemical attack. And what we observe is that when we promote the dissolution in the surface of the rock, we have a more smoother surface, and then this decrease the peak of shear strength during the test. So you have some tomographic images of reconstruction of the surface of the fractures before and after the dissolution, and we have also results for the direct shear stress before and after the dissolution. And so those are evidence of experimental evidence, and we are also working on the numerical part of this work that is build, based on this evidence, numerical models and adapt numerical models from the literature as well, and for this kind of material. And as a general conclusion, we have a numerical tool capable to evaluate integrity of reservoir and cap rocks, consider a number of hydromechanical as the fault reactivation problems, or hydromechanical and chemical phenomena, as in this problem related to reactive carbonates. Special attention should be paid to the rock fluid chemical interactions when a reactive fluid is injected. For instance, mineral concentration can change porosity, permeability, and also geomechanical parameters. Consideration of chemical effects requires incorporations of new variables that are the concentrations of chemical species, new balance equation, that is reactive transport equation, that requires kinetic and equilibrium models for the chemical reactions. Also, we are using in our constitutive modeling the mineral concentrations as a state variable for the mechanical constitutive model, and we were able, for some tests that I showed, to reproduce the formations induced by mechanical and chemical loads. The final message that is the argument that we use to our sponsor in this research is that, of course, they would like to have simulation of matrix and fractures exposed to some acids to expose it to dissolution. But to have this, it is necessary to perform experiments. There are not many results like that in the literature. And it's an obvious, more or less obvious argument, but it worked. We get the support of them, and we are acquiring more equipment for we are acquiring a triaxial test in asteroid that we will be able to induce in a more general stress path the acidification of this material and so on. So finally, I would like to thank the sponsors, and thank you.
Thank you.